Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 1 on Introduction to Logarithms. Now, of all the topics that are in Algebra 2, many of them are review or extension of topics that you did in Algebra 1. But some of them are brand new, and I would suspect that this may be the first time you're going to see the topic of logarithms. So let's jump right into them. Inverses and exponents. Recall that all one-to-one functions have inverses that are also functions. These inverses literally swap the roles of input and output. Exponential functions have very important inverses known as logarithms. So this entire unit, what we're going to be doing is studying the inverse functions of exponential functions, which of course we studied in the last unit. And those inverses are known as exponential. Now, are known as logarithms. Wow, that was good. Now, before we jump into logarithms, I want to give you kind of a little warm-up problem in exercise number 1. Answer each of the following questions. Write an equation that illustrates your answer. Letter A. A base of 2 raised to what exponent would result in 16? Maybe I just should have said, what exponent do we need to raise 2 to in order to get 16, but then I'm going to be saying the word 2 a lot, which is weird. Anyway, so what I'd like you to do is pause the video right now and see if you can figure that out. All right, well, let's just start writing them out, right? I mean, you could sit there on your calculator as well, or put something like a function into your calculator. Let's see, 2 to the second is 4, 2 to the third is 8, and 2 to the fourth is 16. So there it is. So maybe I'll say n equals 4, right? So I would have to have an exponent of 4, right, in order to raise 2 to the fourth and get 16. All right, what I'd like you to do is pause the video now and see if you can do the same thing for letter B and letter C. All right, great. Well, a base of 5 raised to what exponent would result in 125? Well, we know 5 to the second is 25, and 5 to the third, multiply that by 5 again, and that's 125, and so that's it right there, right? So an exponent of 3 would give us 125 if we raise 5 to that exponent. Letter C, a base of 3 raised to what exponent would result in 1/9? Well, that's kind of weird. You know, obviously 3 to the first is 3. And 3 to the second is 9, right? Well, that means 3 to the negative 2 is 1/9, right? Therefore, the exponent we're looking for in this case is negative 2. So in each case, what we were doing is we were trying to figure out the exponent that we would need to raise a base to in order to get a particular result. And believe it or not, that is exactly what logarithms answer. What exponent do you need to raise a particular base to get a particular result? And that is exactly the opposite of what exponentials do, which is they take a base and they say, what will I get if I take this base and raise it to a particular exponent? Let's get into this a little bit more deeply. Finding an exponent. Notice in the first exercise, we are thinking about the exponential process in reverse, answering the question of what exponent would be needed to give a particular result given a particular base. Let's take a look at this from a function perspective now. Exercise number 2. The function f of x equals 2 to the x is shown graphed along with y equals x. A table of values is shown below. All right, and let's just make sure that we're comfortable with this, right? This is a table of values for the function f of x equals 2 to the x. You should feel comfortable with this. 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. When I go into the negative exponents, I'm just getting the reciprocals of these. 2 to the negative 1 is 1/2, 2 to the negative 2 is 1/4, 2 to the negative 3 is 1/8, etc. Letter A. How can you quickly tell that this is a one-to-one function? All right, we've answered this question numerous times. Pause the video now and see if you can give me an answer. Well, one thing you could do is just simply look at the table of values and say there are no repeated y values, right? Remember, a one-to-one function means that every input gets a unique output. There are no repeated y values, okay? Or you could say it passes the horizontal line test, right? Remember that line test says that if I take a horizontal line and I just draw it anywhere on this graph, it's going to hit the graph at most once. All right, letter B. Create a table of values for its inverse function, f inverse of x, and plot the inverse on the same grid. Note the symmetry across y equals x. Well, keep in mind, right, all inverses do is switch the roles of x and y. So it should be extremely easy to create a table of values for the inverse function, because all you have to do is take this table and flip-flop the roles of x and f inverse. So pause the video now, fill out this table, and do the best job you can of plotting the inverse function. I know it's going to be a little bit challenging because you're going to have like an x value of 1/8, an x value of 1/4, an x value of 1/2, etc. But do the best job that you can. All right, well, there's our table of values, right? -3, 1/8 becomes 1/8, -3. -2, 1/4 becomes 1/4, -2, etc. When we plot those, we get something that looks like that. And remember, because it's almost like a trivia question that can show up on a state exam, when you look at a function and you look at the graph of its inverse, they are symmetric across the line y equals x. In other words, if I took this piece of paper and I folded it along that diagonal line, those two curves would lie on top of each other. It's kind of cool. I love looking at the symmetry, but you kind of almost have to turn your head a bit. All right, now let's take a look at letter C, because this is very important. In your own words, describe what the inverse of the function y equals 2 to the x tells you as an output for a given input. So again, look at this particular table of values, this particular table. When there's an input of 1/8, there's an output of -3. When there's an input of 1/4, there's an output of -2. Now keep in mind, these are the inverse of this. So what is that function telling you? Try, in your own words, to write down what it tells you. And this can be quite a challenge. And it's actually one of the things that people tend to gloss over with logarithms, and yet it is the very most important thing of all, which is that what this particular logarithm is telling us, what this particular inverse is telling us, is the power that we need to raise 2 to in order to get the input. So if the input is 1/8, I need to raise 2 to the -3rd to get that 1/8. If the input is 1/2, I need to raise 2 to the -2 to get that 1/4. Sorry, I said 1/2. It should be 1/4. Maybe better yet, with these numbers out here, 8, right? I need to raise 2 to the 3rd power in order to get 8. So what it is telling us is it's telling us, just like in exercise number 1, telling us the exponent we must raise 2 to in order to get the input. And that's really weird, but you can kind of see it, right? Exponential functions take a fixed base and they tell you the result of what taking that fixed base and raising it to a particular input that is the exponent, right? So for an exponential function, the base is set. You know, it's 2 to the x, it's 5 to the x, it's 1/10 to the x, whatever. And what you're changing is the exponent. So what an exponential function always tells you for a fixed base is what the result is by putting the input exponent in, right? And then you get a result. What the logarithm is doing is taking that result as the input and telling you the exponent that you need to raise the base to in order to get that input. And that is a very weird kind of like, you know, weird way of looking at a function, but it's very similar to looking at roots, right? You know, when you looked at the square root of 36 for the first time, you said, well, what number squared gives me 36, right? When I think about the square root of 144, what number squared gives me 144? I'm still looking at it in the context of an inverse. All right, that being said, let's take a look at letter D. What would f inverse of 32 be equal to? Explain. Well, think about what we just said in letter C and see if you can figure that out. Well, right, f inverse of 32 should be the exponent we need to raise 2 to in order to get 32. And again, 2 to the second, 4, 2 to the third, 8, 2 to the fourth, 16, 2 to the fifth, 32. There it is, right? So f inverse of 32 must be equal to 5, and that's because 2 to the fifth equals 32, right? What this inverse is telling us is the power we need to raise 2 to in order to get the input of 32. Finally, letter E. If f inverse of 6 is approximately equal to 2.585, what does this piece of information tell you? See if you can write something down. Pause the video now. Well, again, what this function is telling us is, as an output, is the exponent we need to raise 2 to in order to get the input. So what this is telling us is that 2 raised to the 2.585 will be approximately equal to 6. And in fact, let me test that really quick, right? Let me bring out my calculator. Let me bring a whole new document open, calculator, and let me actually take a look. We've got 2 raised to the 2.585, and yeah, that's just about 6. You know, there's a little bit of a rounding error because that's the approximately thing, but that's fine. All right. Just like square roots, cubed roots, and things like that, logarithms are going to take a little bit to get used to because they are defined in terms of their own inverse functions, which are the exponentials then. In fact, let's get into it right now. Logarithms. Since every exponential function is one-to-one, each has its own inverse of the same base, and that's absolutely critical, same base, known as a logarithm. Let's take a look at its definition. A logarithm of base b gives as its output the exponent that you would need to raise b to in order to result in the input. It is symbolized by log base b of x. All right. Now again, in the last problem where we had y equals 2 to the x, its inverse would be the log base 2 of x. All right. So we're going to keep going back to that. Keep going back to it. Keep going back to it. Exercise number 3. Evaluate each of the following. Justify by writing an equivalent exponential equation. Do as many as possible without the use of your calculator. Then use the general log function on your calculator to check. Fantastic. So letter A, let's do a couple of these together. Letter A is log base 2 of 8. Now again, this one should be pretty easy given the problem we just did. But remember, what this thing is doing, right? Let me just say this is equal to n for a moment. Right? What this is answering is the following question. 2 to the n equals 8, right? What power do I need to raise 2 to in order to get 8? And that happens to be 3. 2 to the third equals 8, right? So the log base 2 of 8 is equal to 3. Now I'm going to show you something on your calculator right now that maybe your teachers are going to hate, but you should know that it's there, right? All modern calculators have the ability to evaluate a logarithm for any positive base. I, of course, can show you this on the TI Inspire. You'll have to find it on other calculators if you don't use the Inspire. Now, on the Inspire, there's a button that says 10 raised to the x. It's right about here, all right? Above it, there's a button that says log. Now, it used to be on older calculators that by hitting second 10 to the x, you would get the logarithm, but only base 10. On the Inspire, however, if I hit second 10 to the x, I get the general logarithm button. So I can put in the base. In this particular problem, it was the log base 2 of 8. And when I hit enter, it gives me the number 3. All right, and that makes sense. Of course your calculator should be able to figure this out. It can certainly figure out that 2 to the third is 8, so it should be able to figure out that the log base 2 of 8 is equal to 3. And we're going to be taking advantage of that a lot on the TI Inspire, so just keep that in mind. Now, I know what some of you are thinking right now, which is, wow, if that thing's on my calculator, I don't need to understand any of this. I can just chuck this into my calculator, and my goodness, would that be a huge mistake. All right, because it is essential that you understand what a logarithm is. Your calculator also has a square root button on it. I still want you to be able to figure out what the square root of 25 is without using that square root button, okay? So make sure that you're using, at the beginning, that general logarithm button to simply check your answers. All right, all that being said, what I'd like you to do is pause the video now and without your calculator, try to figure out the answers to B, C, and D. Don't worry about these yet. We'll get to them in a moment. All right, they're more challenging. But try to figure out the answers to these things and then check them, certainly, using that general log button. All right, well, letter B, the log base 4 of 16. All right, again, that is basically trying to answer the following question. 4 raised to what power gives me 16? And that one's pretty easy, right? That's equal to 2. Now, 4 squared is 16, as simple as that. Log base 5 of 625, that's probably a little bit more challenging. 5 to the n equals 625. By the way, we knew that 5 to the third was equal to 125. We've seen that a few times. 5 to the fourth, that's the one that's equal to 625. So the log base 5 of 625 is equal to 4. I'm very much hoping, though, that you're able to do letter D without the calculator, right? It looks beastly. The log base 10 of 100,000, right? 10 to what power equals 100,000? Well, that should be simple because all you have to do is count the zeros, right? So n in this case is equal to 5. All right, the log base 10, because 10 to the fifth is 100,000, right? Then log base 10 of 100,000 is equal to 5. And again, all of these are very easily checked on the calculator. Make sure that you do get some work with that general log button because it's going to be helpful in a variety of ways throughout this unit. Okay, now let's take a look at some that are a little more challenging. Letter E, the log base 6 of 1/36, right? So what do I have to raise 6 to, right? 6 to the what power equals 1/36? Well, 6 to the n is 1 over 6 squared, which is 6 to the minus 2. So that's going to be -2, right? I have to raise 6 to the -2 power in order to get 1/36. See if you can figure out the remainder of these things. And again, the last two are going to be a little bit of a challenge. See what you can do. All right, well, letter F, very similar to this one, the log base 2 of 1/16. Again, maybe put this in terms of some kind of exponential, right? So we know that 16 is 2 to the fourth. So 1/16 will be 2 to the -4. So that has to be -4. All right. Now, G and H are challenging because the answers are fractional. And in fact, right here, I'm looking for what power I have to raise 25 to in order to get 5. You really have to ask yourself, what is the relationship between 25 and 5? Well, 5 is the square root of 25, right? So, right, 25 to the n is equal to 25 to the 1/2. So in fact, the log base 25 of 5 is 1/2. But maybe the most challenging one, letter H, the log base 3 of the 5th root of 9. Oh my goodness. Actually, let me write this a bit bigger. Now, this one actually goes to show something really great. So let's play around with this a little bit. All right, I'm trying to figure out what I have to raise 3 to in order to get the 5th root of 9. And I should probably immediately ask myself, what exactly is 9 compared to 3? Well, that's 3 squared. Now, of course, the fifth root is the same as the 1/5 power. So that's going to be the log base 3 of 3 to the 2/5. Now, to put it mildly, if I end up getting an expression that looks like this, and I'm asking what power do I have to raise 3 to in order to get 3 raised to the 2/5 power, your answer better be 2/5, right? Because it's literally answering the question, right, for you. You can see the power that you need to raise 3 to in order to get this, and that power happens to be 2/5. All right. So, logarithms, right? You have to be always thinking about them in terms of exponentials, and that gives rise to something called an equivalent exponential expression. Logarithms can be confusing when they are first encountered, no question about it. Sometimes it's easier to think about them in terms of an equivalent exponential expression. And in fact, that's what I was doing a lot of in the last problem, where I kept setting it equal to n. So it's kind of nice to be able to take a logarithmic expression and change it into an equivalent exponential expression. And what I mean by that is an expression in terms of an exponential that says exactly the same thing. Let's take a look in exercise number 4 about what I mean. Rewrite each of the following as an equivalent exponential expression. Letter A, the log base 2 of 64 is equal to 6. So what is this telling you in terms of an exponential expression? Well, what it's telling you is that you must raise 2 to the 6th power in order to get 64. All right? These two statements are saying exactly the same thing. The log base 2 of 64 is 6 is the same as saying 2 to the 6th is equal to 64. Let's take a look at letter B. The log base 5 of 1/5 is equal to -1, right? That is equivalent to saying 5 to the -1 is equal to 1/5. Those two things are saying exactly the same piece of information. Let's see if you can do the rest of these things, and I know they get a little symbolic down here, but see if you can do the rest of these things by writing an equivalent exponential expression. All right, let's do it. The log base 10 of 1,000 is 3 is exactly the same as saying 10 to the 3rd is equal to 1,000. Whoops, is equal to 1,000, not 100. That would be 10 squared. Now, these might look a little bit worse down here, but they really are basically the same idea. The log base 8 of 2 is equal to 1/3 is exactly the same as saying 8 to the 1/3, right, which is the cubed root of 8, is equal to 2. Now, the ones that are very symbolic are right here, and they might get harder to think about because you're like, well, at least up here there were numbers, so I could kind of think about powers and roots and things like that. The log base 4 of x is equal to y, right? That is going to say that 4 to the y is equal to x. I remember very few things about my high school math experience because it was a long time ago, to be very clear. But one thing I remember is my high school math teacher saying, look, if you ever have a logarithmic expression and you want to convert it into an equivalent exponential expression, take the base and scoot it over and get rid of the word log, right? So 4 to the y is equal to x. And that is particularly helpful, especially in a situation like this, right, where I can then kind of zoom my base over here and b to the n is equal to m. Now again, if you just think about what logarithms are doing, right, like for instance here, and let me get rid of this just to kind of illustrate, right, log base 4 of x is equal to y. What that is giving you is the power you need to raise 4 to in order to get x. So what it gives you is the power that you need to raise 4 to in order to get x. Likewise here, when I do the log base b of m is equal to n, it's giving me the power I have to raise b to, that's a power that I have to raise b to in order to get m. But it's also kind of convenient to do the slide over method, right? Where I can just be like, oh, slide the 8 over here, 8 to the 1/3 is equal to 2. Anyhow, nice little trick there, especially if you're confused about logarithms, which a lot of people are at the beginning. Let's talk about one more thing with logarithms, and this whole unit is devoted to them, so we're going to keep harping on all this stuff as we go through it. It is very important to understand the inverse nature of exponential and logarithmic functions. Let's take a look at that in exercise number 5 with a little composition of functions. Exercise number 5. If f of x equals b to the x and g of x equals log base b of x, then evaluate each of the following. Letter A, g of f of 3. Well, let's do this one together. Let's remember how composition works, right? G of f of 3 means that we're going to take 3 and we're going to substitute it into f. We're going to get an output. Then we're going to take that output and substitute it into g. So f of 3 is equal to b to the third. And you might be like, well, that's not very helpful. But then what I'm going to do is I'm going to take this and I'm going to substitute it into g, and I'm going to get log base b of b to the third. Well, what is the log base b of b to the third? Pause the video right now and see if you can figure out what that is. Well, log base b of b to the third answers the question, what do I need to raise b to get b to the third? And that's going to be 3. And notice, right, what happened. They're inverses of each other. So g of f of 3 ends up being 3 because 3 goes into f, gives us an output. Whatever that output goes into g, and goes full cycle back to the input. Try letter B and letter C and make sure that pattern holds. And in fact it does, right? G of f of negative 1, f of negative 1 is going to be b to the minus 1. G of b to the minus 1 is going to be log base b of b to the minus 1, and that's negative 1, right? And finally, g of f of x is going to be g of b to the x, and that's going to be equal to the log base b of b to the x. And what do I have to raise b to in order to get b to the x? I have to raise it to the x power. You can literally think of the logarithm and the exponential canceling each other out and bringing you right back to where you started. And that's really critical, because that's what all inverses do. All inverses, in every mathematical context, sort of take an input, map it to an output in one direction, take that output, and bring it right back to the input in the other direction. All right, let's wrap this up. Exponential functions are exceptionally important in math, science, economics, and a lot of other things. And because they're extremely important, their inverses must also be important. Those inverses you've never dealt with before, but now are going to start to and work on them throughout this unit. Those inverses are known as logarithms. Every single exponential function, y equals 3 to the x, 10 to the x, 1/2 to the x, what have you, has a logarithm of the same base that is its inverse. And that logarithm is always answering a very strange question. It's answering the question, what exponent do I have to raise the base to in order to get or result in the input to the logarithmic function? So the log base 2 of 32 gives us as an output 5 because 2 to the 5th is equal to 32. I want you to really think about logarithms in exactly the same way that you thought about square roots when you first heard about them. When you first heard about square roots, you always had to think about what number squared gives me the number underneath that square root symbol. Logarithms are very, very similar to that. Now we're going to work through them throughout this unit, so make sure to really work hard on the homework. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.